On September 8, 1900, Galveston, Texas operated as the fourth largest city in the state and a principal Gulf Coast commercial port. The city occupied a barrier island approximately 27 miles long and less than 3 miles wide at maximum, positioned directly on the Gulf of Mexico, with mean elevations between 4.5 and 8.7 feet above sea level. No seawall or coastal protection structure existed. The urban core contained wood frame residential structures, brick commercial buildings, and approximately 37,000 permanent residents. Weather observations were conducted by the U.S. Weather Bureau from a downtown station. Late summer tropical activity in the Gulf was considered routine. Galveston Island extended parallel to the Texas coastline, with the Gulf of Mexico to the southeast and Galveston Bay to the northwest. Maximum ground elevation across the populated areas measured 8.7 feet above mean sea level. Most residential districts occupied elevations between 5 and 7 feet. The island's width averaged 1.5 miles in developed sections. No natural high ground existed. Urban construction consisted primarily of wood frame buildings on pier and beam foundations. Brick structures concentrated in the commercial district along the Strand. The city possessed no engineered coastal defenses. Drainage relied on surface flow and minimal storm sewer capacity. The population density in residential blocks exceeded 15,000 persons per square mile in central areas. A tropical disturbance was first observed over the central Atlantic in late August 1900. The system tracked westward across Cuba on September 4 and 5, producing heavy rainfall but limited wind damage. Upon entering the Gulf of Mexico on September 6th, the storm intensified rapidly over warm surface waters exceeding 85 degrees Fahrenheit. The U.S. Weather Bureau tracked the system's northwestward movement toward the Texas coast. On September 7th, warnings were issued for the Texas coastline, though storm surge magnitude could not be forecast with available methods. By the morning of September 8th, the Hurricane Center was positioned approximately 250 miles southeast of Galveston, advancing at 15 miles per hour with sustained winds estimated at 120 miles per hour. The hurricane's wind field generated an offshore surge through sustained easterly and southeasterly winds exceeding 100 miles per hour across a fetch of over 200 miles. The shallow continental shelf gradient along the Texas coast, with depths less than 30 feet extending 50 miles offshore, amplified wave setup and wind-driven water accumulation. As the storm approached on September 8th, tide gauges recorded water levels rising 4 feet above predicted astronomical tides by mid-morning. The surge wave propagated westward along the coast and northward into Galveston Bay. Peak surge height at landfall was later estimated between 15 and 20 feet above mean sea level, exceeding the island's maximum natural elevation by 7 to 12 feet. Storm surge began overtopping Galveston's southeastern shoreline at approximately 3 p.m. on September 8. Water advanced across the beach and low-lying residential streets within 30 minutes. With no coastal barrier, surge flow entered the urban grid through multiple points simultaneously. Wind speeds exceeded 100 miles per hour, generating wave action atop the advancing surge front. By 5 p.m., water depths in southern residential districts measured 5 to 8 feet. The rate of surge advance was approximately 1 to 2 feet per hour in elevation. Northern sections of the island experienced water entry from Galveston Bay as wind-driven surge pushed across the lagoon. Escape routes to the mainland via rail and wagon bridges became impassable by 6 p.m. Sustained winds exceeding 120 miles per hour imposed lateral loads on vertical building surfaces ranging from 40 to 70 pounds per square foot. Wood frame residential structures experienced progressive failure, window breakage, roof removal, wall collapse. Debris from failed structures became wind-borne projectiles impacting adjacent buildings. Brick commercial buildings in the central district sustained roof loss and upper-story wall failure. Structures on pier and beam foundations experienced flotation and lateral displacement in surge currents exceeding 10 feet per second. By 8 p.m., an estimated 2,600 buildings had experienced total structural failure. Debris fields accumulated in surge flow channels, forming obstructions and battering rams against remaining structures. Telegraph lines to the mainland failed by 6:30 p.m. on September 8th, eliminating external communication. The 3 bridges connecting Galveston Island to the mainland were rendered impassable by water depth and structural damage before 7 p.m. Municipal water supply ceased as pumping stations flooded. Electric power distribution failed citywide by 8 p.m. Fire suppression capability was eliminated. Medical facilities sustained structural damage and flooding. Emergency shelters and larger buildings reached capacity, with occupant densities exceeding 200 persons in structures designed for 50. No evacuation was physically possible after 6 p.m. Rescue operations by boat were limited by wind speeds exceeding safe navigation thresholds and zero visibility in darkness and rain. Peak storm conditions persisted from approximately 8 p.m. on September 8th until 2 a.m. on September 9th, a duration of 6 hours. During this period, sustained winds remained above 100 miles per hour, with peak gusts estimated at 145 miles per hour. Storm surge maintained elevations of 12 to 15 feet across the southern 2/3 of the island. Wave action continued throughout the night. Persons trapped in failed structures or displaced into open water experienced continuous exposure to wind, water, and debris impact. Ambient air temperature was approximately 78 degrees Fahrenheit. Water temperature was near 82 degrees Fahrenheit. No organized rescue capability existed during the peak period. Survivors reported immersion durations ranging from 4 to 10 hours. Post-storm surveys documented 3,600 residential and commercial structures destroyed, representing 3,636 buildings confirmed as total losses. An additional 2,600 structures sustained major damage. The death toll was estimated between 6,000 and 8,000 persons, representing 16 to 22% of the pre-storm population. Casualty rates varied by elevation and building type. Ground-level wood frame residences in southern districts experienced mortality rates exceeding 50%, while multi-story brick structures in the commercial core showed rates below 5%. Approximately 10,000 persons were rendered homeless. Infrastructure losses included the complete destruction of port facilities, rail lines, water distribution, and electrical systems. Total property damage was estimated at $30 million in 1900 currency. Debris removal operations began on September 10, 1900, and continued for 8 months. Bodies were initially recovered and buried at sea. Later, mass cremation of remains was conducted on site. The U.S. Army Corps of Engineers initiated city reconstruction with a planned grade-raising project, elevating the entire urban area by 1 to 17 feet through hydraulic fill operations completed between 1902 and 1910. A concrete seawall was constructed along the Gulf-facing shore, beginning in 1902. The initial section measured 3.3 miles long and 17 feet above mean low water. Galveston's population recovered to approximately 36,000 by 1910, but the city never regained its pre-1900 position as the dominant Texas Gulf port. The U.S. Weather Bureau official report, issued in 1901, classified the storm as an extreme hurricane, with estimated central pressure below 27.5 inches of mercury, 931 millibars, and maximum sustained winds of 120 to 140 miles per hour at landfall. Modern reanalysis categorizes the event as a Category 4 hurricane on the Saffir-Simpson scale. The 1900 Galveston Hurricane remains the deadliest natural disaster in U.S. history by confirmed fatalities. Engineering assessments identified storm surge as the primary destructive mechanism, responsible for approximately 80% of structural failures and 90% of fatalities. The event established surge height and coastal elevation as critical parameters in hurricane risk assessment and led to standardized coastal defense engineering practices.